Hello to everybody. I'm very happy today that we at least managed to organize the lecture, online lecture, unfortunately, but still a lecture that was organized in occasion of Thomas Savage Getson retrospective in Museum of Contemporary Art, and which was opened and then closed due to pandemic, and then reopen again, and it will be possible to see it until 14th of June. Namely, Thomas Savage Getson, thanks to the initiative of Association Container, Olga Majsen-Lin and Sunčica Ostojić, had the great opportunity to be part of the residency in CERN. And that was actually the reason why we invited the guest from CERN, curator Monica Bello, and that collaborate with artists and make this link between artist and scientist with whom Thomas Savage Getson collaborated, physician Michael Dozer. But before we start with the lecture, I would like just for all these people who has not a possibility to go on Thomas retrospective or doesn't know anything about Thomas' work, just to go on little walk through the exhibition in the museum. So I will switch to a small video which will present you the exhibition. Just a second. Yeah, actually, Thomas Savage Getson is one of the most radical artists in sense that he's from the beginning, from 1994, he's dealing with emptiness, with complete emptiness, with and actually when visitors come into the space, he confronts with the absence actually, and his expectation are in some way betrayed. But staying in a space, he will realize that there is no emptiness. Actually, everything happened and many things happened. And actually, there are many gestures that happened there. In sense that Tomo is using the whole space as the media. The space is media in the zero level, but also we can say that institution, first of all, institution of museum is his media, but also there are some other gestures that we confront, that something is happening in the space and time when we are visiting the show. But for example, the light is changing because somebody enter in a space of architects on some other place, or when some passenger came in taxi, then humidity in space is changing. Also, when temperature in Zagreb change, then this line, this tape is going or down or up to show that we can enter or not enter into the space. And also the space is full of some barriers. Here is one glass in one corridor, and actually passenger can't should stop and change his way. In this retrospective, we can also ask the question about what is it a real retrospective? Yes, this is real retrospective, because he show us the works that happened once in actually, this is 46 years of his artistic practice, full of various gestures that we can connect with the gestures of actually artist that was that started in the second half of 20th century, neo-avant-garde artist, and also the artist that connected with conceptual art, but also comparing all these gestures that are dealing with mocking the gallery, the institutional space, we can see that there are also some other gestures that that Tom explores some other possibilities, and asking question what's actually art can a piece of art can be. And one aspect is very important for his work, that is the dematerialization, act of dematerialization. And also something goes together with act of transition. For example, he is using a glass from some gallery in Brussels and make the glasses of that glass from the gallery that people use during the opening for the wine. And the same glass he used after make the dust and melt with the color. Excuse me, we finished with the video. I will go a little bit. Okay, so we will stop share it. And so the video stop in one moment on the work that Tomo realized in CERN. And actually, this is one of his most radical works, also connected on some way with the tradition of neo-avant-garde art, in sense that all these artists like Yves Klein, Manzoni, Duchamp have always this attempt to go beyond the matter. And actually, Tomo did in collaboration in this residency, this idea to make this idea as realized metaphor. Actually, he realized that this idea to go beyond the matter. And of course, I would like to actually we wanted to present this ambient where artists collaborate with scientists. And Monica Bello, she's more than 15 years, she's making this multidisciplinary connections between artists and scientists from various profiles. And now she's head of Art in CERN program. And so, Monica, please tell us something how that starts, all this, and this collaboration with Tomo. And actually, we are very curious about this program in your institution.
Thank you, Radha. Thank you, the museum team, and thank you, Container, as well, for the bringing our work and giving the possibility to Croatian artists to participate in our programs back in 2017 through Accelerate. Well, I'm going to give you a bit of context, and I hope this ends up bringing all of us together to the exhibition spaces that you just show us, that are empty. But if there is something, it makes me realize through your video, by watching your video, it makes me realize what a great choice was to invite Tomo to think and investigate his ideas of beyond matter in the laboratory. I'll give you a bit of context, and for that I'm going to play my PowerPoint, which is going to help me to show you the places and hopefully the faces as well, the dynamics, the experiments, the community that form CERN. I'll share my screen, which is now, should be sharing. Like that. Okay. So I'll start by giving a bit of context, but from the beginning of the 20th century where we are now. Why are we talking about art and science and technology and the conversations that happen between communities at laboratories and at the museum spaces? We know that over recent years, several scientific institutions have nurtured novel models of dialogue and cooperation between artists and scientists. And the museums and art centers and organizations, cultural organizations at different forms have increasingly been incorporating art and science explorations into their programs. At the same time, scientific organizations have started to experiment the connection with creative communities. What is creativity is becoming a big question to all of us. And this was with a clear intention to move to more innovative forms, models, methodologies, especially those that are a bit move beyond the mere outreach and communication goals. From an academic context as well, we see how several schools and universities are testing art and humanities programs in which there is a clear interest in taking insights from science studies and running them back into the cultural, artistic, and humanities areas. In my talk today, I will speak about what is to spend and to be part of a lab. And in particular, I like to think with you what are the conditions and the implications of artists working in these unique and complex research environments? What forms of creation take place in a highly specialized environment and community? And at some point we'll reflect also together. I like to share this with you, thinking about what common grants can be shared in order to negotiate the limits of contemporary creativity through different fields and experiences. It's not new that artists have been inspired by the concepts of science. In the first decades of the 20th century, when the field of physics shifted into the quantum paradigm, artists were already expressing the influence of the language of natural science in their works. Around the time when Max Planck wrote his paper, The Elementary Quantum of Action, which sets the foundation of quantum physics and add the term quanta to our vocabulary, modernist poets aspire to a genuinely quantum mechanical view of their poetic act, aiming to demonstrate that art, poetry, and science physics were the same thing. We are seeing a quote of T.S. Eliot that in 1919 decided to explain the prehistory of a poem in the poet's mind by the reaction of sulfur dioxide and oxygen in the presence of platinum filament. He said, when oxygen and sulfur dioxide are mixed in the presence of a filament of platinum, they formed sulfurous acid. This combination takes place only if the platinum is present. Nevertheless, the newly formed acid contains no trace of platinum, and the platinum itself is apparently unaffected, has remained inert, neutral, and unchanged. The mind of the poet is the shred of platinum. We must read these expressions as cultural assumptions built into a revolutionary time in science. The use of scientific jargon as metaphors reveals a new insight into artistic practices in this time of history, a moment in which quantum mechanics saw a rebirth of physics. From a perspective of the scientist, sympathetic to a broader perspective, it's well known that Niels Bohr, a founding member of CERN and one of the pioneers of quantum mechanics, theorized that complementarities exist in different forms of human cognition in both art and science. These first expressions paved the way for future advances in cross-disciplinary thinking. The experimentation of ideas that connect art and science notions continued during over the last century in all the disciplines of the arts, from the visual arts, literature, philosophy, you name it, design, even architecture, gaining strength in parallel to the positions of science, evolving theoretical discussions, and new models of scientific making. Half a century later, while Europe was recovering from the destruction of the war, physics itself came to terms with a new model of scientific research and experimentalism, with technological challenges that demanded a new setup for the physics laboratory. Hardware, cryogenics, mechanical and structural engineering, electronics, and informatics became the new landscape for the old research center and the sign of identity for the new. Founded in 1954, CERN, the European Organization for Nuclear Research in Geneva, was born in this moment. It is now at the end of the Second World War, European science was no longer world class. And following the example of international organizations, a handful of visionary scientists imagined creating a European atomic physics laboratory. Rolf Daumtry, Pierre Rouget, and Lev Kowarski in France, Edoardo Amaldi in Italy, and Niels Bohr in Denmark were among these pioneers. Such a laboratory could not only unite European scientists, but also allow them to share the increasing cost of nuclear physics facilities. Physicists and engineers are probing at CERN the fundamental structure of the universe, using the largest and most complex scientific instruments ever existed, a complex of particle accelerators and detectors. When the laboratory was founded, the structure of matter was a mystery. Today, we know that all visible matter in the universe is composed of a remarkably small number of particles, whose behavior is governed by four distinct forces. And CERN has played a vital role in reaching this understanding. With goals such as uncovering the true nature of the universe, matter, and reality, it's not surprising that artists are attracted and were attracted from the beginning of the laboratory to this environment. Such was the case of American artist James Lee Byers, whose trace can be found at CERN archives in the 70s. And he was, and still is, the only artist to appear on the front page of the CERN Courier. You can see at the bottom, at the right bottom of the page, the caption of the picture that says, "One of the visitors who brought some color in the CERN corridors during the summer." His photograph here in the ISR site with the experimental hall, Al1, and water tower in the background. These places still exist at CERN, and it's very, very interesting to see James Lee Byers standing there trying to figure out the big questions of matter and the universe, and why we are asking these questions. One of the, I would say, the pioneers of antimatter thinking in the arts was Gianni Motti. In May on the 20th of May in 2005, he compared himself to a proton. And after going down into the Large Hadron Collider tunnel, which was empty at that time, it's a circular tunnel of 27 kilometers of large, he walked the whole distance in an accelerated pace of 5 kilometers per hour. It took him about 6 hours. In comparison, particles turn around the ring 11,000 times in 1 second. This experiment is reported via a tracking shot that follows the artist who walks along the world's largest accelerator, empty and dull at the time. And this made him an anti-moti. This artwork is still shown in the gallery Perrotin, who supported the production of the piece in 2005. The tunnel is like that today. This is part of the instruments of experimental physics developed at CERN for pursuing the main goal, as I said before, understanding the fundamental constituents of matter and the origins of the universe. They take multiple forms and shapes, from discrete microcircuits to the vast scale of the Large Hadron Collider that you are seeing, which was built between 1998 and 2008 in collaboration with more than 10,000 scientists for at least 100 countries. Located at around 100 meters below the ground, we can say that these beam tubes that you are seeing are the emptiest space in the solar system, at times 100,000 times hotter than the sun or colder than outer space. As Fiona Crisp, artist and researcher from Newcastle, says as part of her research project Material Site, she says that with advanced science and technology and its reliance on abstract data, and with the accelerating impact of human activity on the planet, we live in new scales of size and speed that we cannot easily comprehend. If so much knowledge comes through scientific instrument, how can we make sense of it within our own experience? Well, this takes me to explain what we do at Arts at CERN. On entering the lab, it immediately becomes clear that for an artist, it will not be straightforward to comprehend the broad range of experiments, their scale and function, and the models that might be represented through deeply specialized theoretical models of our world, drawn in sometimes mathematical language. In 2011, the former Director General Rolf Hoyer promoted and supported the CERN cultural policy thanks to the proposal of curator Ariane Coec. And this marked the beginning of the activities of Arts at CERN, which is today the official art program of the lab. With Arts at CERN, we foster new expert knowledge in the arts by extending artist practice in connection with particle physics and engineers at CERN. We offer time and space for the artists to come to the laboratory as residents and as researchers, and to explore ideas related to fundamental science. Then we often ask ourselves, why do artists want to spend time at the lab and what we can offer to them? We think very thoroughly about these changes. We want to move away from the communication of science that can be supported by artists, or the using science for technical dilemmas in the arts. To foster significant exchanges between art and physics, we set up models of collaboration and dialogue that are leading today the art and science discussions. By engaging directly with the theory and methodology of answering fundamental questions, artists enrich and inform their practice and the ways in which they can inform their ongoing lines of questioning. To make sense of the intangible complexity of knowledge discovery and to make the invisible visible, At CERN also, the artist can see their work through the disciplines of others. How do we do this? We do it with a set of programs, different schemes, that since the beginning of the program in 2011 until different phases, we develop residencies, art commissions, and lately exhibitions. And each program has a core activity, which is research and involvement with the CERN community. So we have the light residencies. This is the long residency of 3 months. Accelerate residencies that are a country-specific award for artists from different geographies to assess the residencies programs for 1 month. And guest artists, usually artists that cannot commit to long periods and are focusing to a new commission, to develop new commissions. Since 2015, when I arrived to the program, we began to develop the scheme of art commissions, fostering artistic production that result from the dialogue between art and physics and in connection with the scientist at the lab. And before we go into Tomo, we also are involved in exhibitions globally with global partners that are hosting our art commissions or are co-producing with us new artworks. In 2017, we worked with a container in Croatia, and with the support of the Ministry of Culture, Container and us, Arts at CERN, put together an open call for Croatian artists to carry out artistic research in this field. The artist selected would spend 1 month with us, during which time he would be introduced to the different aspects of the research conducted here. Dialogue and discussion of ideas was very important during this time, and the connection and information of the great scientific discoveries and today's scientific research. Engaging with theoretical notions of time and space, as well as encountering the practical cutting edge of engineering using the experiments and others. Our residencies are a framework for setting up tools, methodologies, questions. And Tomo Savage-Gekan came with the idea of the emptiness, appearing to display nothing in his works, which was rather surprising to us. Even in his proposal, he proposed to do a new Untitled project based on a previous project that was focusing on time and space, the question and definition of art, the role, spectators in the art, the museum spaces. As Elena Filipovic, the curator of the Kunsthalle Basel, said, Tomo deliberately inconspicuous projects deny the primacy of the visual without retreating to the pure ideation of conceptual art. His art is intimate, concerned with experience, often spread across 2 places or temporalities. Seeing Tomo at the lab seemed a great match to us because the concepts of emptiness, the concepts of space, of time are so powerful, and everything physicists and physics in general is research about. So we thought we could support his research, and he set up a methodology in which he was using an existing structure of work, his entire career dedicated to identifying the roles in art, the roles in empty spaces, and a second stage during the residency in which he could investigate and exchange with some scientists to better understand the scientific implications of these terms that were over-conceptualized in our culture, and how they could be conducted artistically at CERN. During the residency, he gained content by going to different sites, experiments, talking to scientists, engineers, staff, understanding the history of the place, of the community, going into the archives, discussing with theorists, as well as understanding the materiality and the technical approach, and devoting time and to dialogue and assess the place, formulating a final definition of the project as it would happen. It was not a coincidence that he ended up in the antimatter factory. Really, there is not better match for his work, and I'm so pleased that this primordial question about materiality found himself playing ideas and experimenting with the idea of antimatter. The antimatter factory is one of the most attractive environments and conceptual spaces, epistemic spaces for many artists that come to CERN. And I'm pleased to see that he transferred this idea and the research that came with it to the museum in Zagreb. From a curatorial angle, Arts at CERN attempts to respond to a model of institutional cultural practice that is not in a museum, is in a scientific lab, but that nurtures and supports artist engagement with the big questions of our time. And science is so important that we cannot not open the doors to the artists to explore the ideas and the materiality that are inside the labs. The artists are invited to confront and respond to an age of accelerating scientific and technological development and become active with the dynamics and complexities of these places in the most radical way. I'm going to leave it here because my time is running out, and thank you very much, Rada.
Yeah, it will be nice that we are in Zagreb here in the museum, but still it's nice that we are here. And unfortunately, I can't see the questions. I suppose perhaps somebody will have some question that can type, but I can't see this. I don't know if Michal, can you see this reactions of public? Or
no, I don't see it either.
Good. So we will continue. Actually, Tomo had at least after having idea, somebody has to realize that idea, of course. And who can do this? Then a physicist who is dealing with antimatter as a professional. And I'm happy to present you today Michael Dozer, who is working in CERN, but also who is also involved a lot with working with artists, which is very interesting to help them because I suppose and I believe that in this collaboration there is advantage for both sides. I don't know if it is, but or only artists have some how to say benefits from science. But I suppose it can be also attempt for you as a physicist to collaborate with artists.
Absolutely, and I think Monica said it very beautifully in the words of T.S. Eliot. The artist can be the catalyst for technical, scientific, conceptual breakthrough. So I won't be talking about that afterwards, but I will be talking a lot about the science and a little bit about the art as well.
Okay, let's go then.
All right. So if we talk about Tomo Savic's work, and as you've heard, it has a lot to do with emptiness, with space, with empty space, with dematerialization, with going beyond matter, with transformation and transmutation. the natural place to look for the kinds of concepts that can play a role in these questions is really antimatter. And so I will be talking in the next 30, 40 minutes about antimatter, trying to give you an idea of what antimatter is, why it's so interesting for us as scientists, but also for artists, how we look at it, and some of the philosophical questions that arise from the way we look at it. And this naturally leads in then afterwards to a number of artists' works that look at antimatter and the consequences of what antimatter is on our existence, and in particular, Tomo's work, using antimatter, which poses actually many of the most interesting and deepest questions. So in order to start, I will talk a little bit about antimatter, its disappearance act from the universe and from our lab. And the real question when you start talking about antimatter is to try to understand what it actually is that we're talking about. And I call this a little bit rooting for the underdog. Antimatter has a very bad reputation. You'll see in a minute why. And the point here is that if you think about the universe, the whole universe, there's a conceptual and fundamental problem, which is that it's not empty. Now, normally people would be happy that the universe is not empty, because without that, we would not be around to exist. But in fact, there's a problem at a deep level, and that problem has to do with what theory predicts. Our theories, our descriptions of the universe that CERN has contributed to quite substantially in the last 65 years, this theory is not able to explain why the universe is not empty. It should be empty, and it should be empty simply because every time a particle, matter, is produced, an antiparticle, its antiparticle, is produced as well. Matter and antimatter particles are always produced in pairs. Here on the left image, you can see the pair production of an electron and an anti-electron. Here and here, an anti-electron and an electron. In this image, you see many, many pair productions of electrons and of anti-electrons. Every time they balance, every time they're created in pairs. And in fact, this is something that should have happened right at the moment or right after the moment of the Big Bang too. Should have been equal amounts of matter and an antimatter. And so you expect, based on the symmetry that exists between matter and antimatter, a symmetric universe, 50% matter, 50% antimatter. Now, if you look at the universe, you take a picture of the sky, everything you see, the hundreds of billions of galaxies inside which there are hundreds of billions of stars, all the matter, all the dark matter, all the objects that are flying around in the universe, all of this is matter. If you try to look at the same universe through a filter that only selects out the antimatter, you would see absolutely nothing. None of the stars, none of the galaxies, none of the objects that we see in space are actually antimatter. Everything is matter, although we expect equal amounts of both. And this is a huge problem. How can you have lost? How can all this antimatter have been lost? How can you lose half of the universe? In fact, the only way to explain something like this is to say that antimatter, which is a mirror image of matter, is not a perfect mirror image of matter. There's a mirror, a conceptual mirror, that mirrors matter into antimatter. And this conceptual mirror is slightly flawed. Matter and antimatter are not mirror images of each other, but in fact, one is the evil version of the other one. And since my activity deals with working with antimatter, you know where my sympathies lies. I root for the antimatter, which has disappeared and was murdered in some way by the matter at the moment of the Big Bang, leaving only a tiny excess of matter over antimatter, all the antimatter having disappeared. In other words, rather than having a symmetric universe, which starts out with energy transforming into mass, and this mass being either matter or antimatter, via E is equal to mc squared, what you actually end up very shortly after the moment of the Big Bang is a slight excess of matter, with all the matter and all the antimatter having annihilated itself, but with a slight excess of matter having been produced right at the moment of the Big Bang, which means that the universe, instead of being symmetric, as we would expect from our theories, is actually asymmetric. It's imbalanced, and this imbalance leads to an excess of matter. Now, this imbalance is something that we don't see in the physics that we're exploring. If you look at the universe right now, you can try to see where such an imbalance could possibly happen. This is a compressed view of what the universe looks like in time. On the right-hand side here is the present, where we're looking at the universe and looking backwards in time towards the Big Bang. This is the moment of the Big Bang. And as you look backwards in time, as you go to the moment of the first formation of stars, about 300 million years after the Big Bang, to the first formation of atoms, about 300,000 years after the Big Bang, you get into the regime of where individual particles and antiparticles, about 1/10 of a billionth of a second after the Big Bang, were interacting with each other. And already at this very early time, an imbalance must have existed. There must have been a slight excess of matter over antimatter. So we must go even further back in time to this second ring in time where an excess, a deviation from symmetry, a mirror breaking, a symmetry breaking must have occurred. And in order to try to get a picture of what happened at that point, the only tools we have are very simple. It's like investigating a crime scene. And in this case, there's a crime scene investigation that we can do now by looking at the universe and looking at how the universe is currently behaving and what it is composed of. And we can also go back to reenact the crime scene, reenact the moment of the Big Bang, and try to understand what actually happened at that moment or shortly after the Big Bang to see if some imbalance occurs at that moment that then snowballs into everything that we see now in the universe. So in terms of the crime scene investigation, we can only look at the universe, and this means looking at antimatter or for antimatter in space. And I said before that if you apply a filter to the universe, you can see the antimatter. This is not quite true because antimatter looks exactly the same as matter. There's no way to differentiate matter from antimatter by looking at it. The only thing that you can do is take this reaction that occurred and that transforms energy into particles and antiparticle pairs, to run this reaction backwards and to make antimatter meet matter. And when that happens, energy is released. And this energy you can see. This is the only signature that allows completely unambiguously detecting antimatter. So one can look for this energy in space. And if one looks at the universe, the whole of the universe with a telescope and looks only for this particular energy, as was done by the integral satellite, it's possible to see the presence of antimatter in the universe where it has annihilated. So this, for example, is an image of the antimatter matter annihilation that is taking place at the center of our own galaxy, right at the core of the galaxy, right around the central black hole, due to processes that we don't currently understand. This is still an area of very active investigation, but this is also the only place in the universe where we can see matter-antimatter annihilation, simply because it's so close and because this annihilation is so weak. It's only a very, very small signal. There's only a small amount of antimatter annihilating there. The other possibility is to try to look for things that rain on us, coming from outer space in form of cosmic rays, and measuring for every single particle that goes through an apparatus called the alpha magnetic spectrometer, which is sitting here on the International Space Station, measuring every single particle going through it, and for each individual particle determining whether it is a matter particle, protons, electrons, helium nuclei, or antimatter, antiprotons, anti-electrons, or perhaps very, very, very rarely antinuclei. And by studying these antiparticles and looking for antimatter in the universe, one can hope to try to get enough clues to understand how an imbalance could have happened. This is, of course, an observational approach, but there's a more direct approach, which is to study antimatter by making it and then looking at it in the lab, going back to the moment of the Big Bang, reenacting the crime scene, and looking how antimatter behaves. This is an aerial picture of CERN. Geneva is off to the right-hand side. This is the airport, which is currently amazingly quiet, like almost all airports at the moment. And this is the 30-kilometer underground ring that Gianni Motti walked around. You could see the 30 kilometers underground if you could see through the ground. This is about 100 meters under the ground. And here in this area is the center of CERN. This is where all the control systems happen, where all the experiments run that are not directly sited on the Large Hadron Collider. And there's a tiny little space here, which is where all the antimatter made at CERN is looked at and studied very carefully. What these experiments on antimatter are trying to do is look for the suspects. There are 4 suspects in this crime scene that have been looked at in the past or currently being looked at right now. Coming from the area of neutrinos, coming from the area of symmetry violation, coming from a more complete, more fundamental symmetry violation, and coming from the area of gravity. And the interesting thing is that all of these questions, all of these investigations take place at very low energies compared to the very high energies that this big accelerator produces. I'm going to focus on just 2 areas. This symmetry violation, which basically is the flawed mirror that we might be looking for, and gravity. In order to look for a flawed mirror, what you need to do is study antimatter very, very precisely, ideally trap it. And you can see here a wonderful can. I'll show you what it really looks like in a moment. And the idea is that if you have antimatter, in particular anti-atoms in such a can, you can try to measure the color of the light that this antimatter emits and compare it to the color of light emitted by normal atoms. And since the only atoms that we can make of antimatter are antihydrogen, an antiproton with an anti-electron, this can be compared to the light emitted by hydrogen. This is what that light should look like, at least if you look at what Hollywood thinks about this. This is a still from the movie Angels and Demons. And here in the center would be a sphere, a ball, a cloud of antihydrogen atoms. It's not too far from reality because the color that you expect it to emit is in the ultraviolet. And this is what the real trap looks like, or an approximate image of what the real trap looks like, where you need very powerful magnets, ring magnets, and these very strange coils to contain a cloud of anti-atoms inside vacuum, inside empty space, as empty a space as you can make, because antimatter, if it will touch matter, will immediately annihilate and disappear. So for somebody who is interested in empty space and elimination of matter from space, antimatter has a very attractive component. It destroys matter, and after this destruction, both matter and antimatter will have disappeared, leaving nothing behind, no objects inside that space any longer. What the experiments that do these comparisons look like is this. This is a very small experiment. It's a magnet, a very powerful magnet, superconducting. You can see different liquid nitrogen, liquid helium doers that are needed to make this magnet superconducting. But in the heart, it's just a little trap and a laser firing at the atoms that have been trapped. The second thing you can do with antimatter, in addition to measuring its color, in the case of antihydrogen atoms, is try to measure how it behaves under external forces like gravity. So you want to measure the fall of antihydrogen, of antimatter. It has to be a neutral system like antihydrogen, simply because if it's charged, electric fields, magnetic fields, the Earth's magnetic field will impose a much, much stronger force than gravity itself. Gravity is extremely weak. And so the only way you can study gravity on a system is to have a neutral system, either balls of matter, which are inherently neutral and where you can drop a ball of matter and a ball of antimatter, or cannons by which you can shoot at different speeds, fast or slow, neutral antimatter. And the effect of gravity will be to pull the atoms away from a straight line downwards if gravity works for antimatter the way it works for matter. And the question here is whether we can see a difference between the way gravity affects matter and the way it affects antimatter. This is the experiment that is doing that. This is the cannon, in a way, shooting antimatter, or actually this is the magnet again, which contains the cannon, which is here on the right-hand side. Antihydrogen atoms, atoms of antimatter, are made in these little rings where antiprotons are held and anti-electrons are brought in through a complex interplay of anti-electrons interacting with matter, being manipulated by lasers, forming antihydrogen, and then the idea is to shoot these atoms out as through a cannon. If you do that, then the trajectory of these atoms is going to be straight if there's no gravity. They do not fall without gravity. They fly on a straight line, and you need to know where they hit. You need to have a reference, and so you need some kind of pattern on a wall that tells you what you expect, where they should land if there is no gravity. What you then need to do is shoot them more slowly. And if you shoot them more slowly, of course, gravity has a chance to pull them downwards, to shift them vertically by a tiny amount, 1/100th of a millimeter. And where the antimatter then hits the matter wall, the antimatter and matter will annihilate. And this produces fragments, particles, energy emission that can be detected. With a single annihilation, you cannot say anything. What you need is many, many, many annihilations. And each one of these produces an annihilation star, which you can measure. And if you see a shift of the average of the annihilation stars with respect to your reference pattern here, or here with respect to this reference pattern, then you can measure by how much gravity has affected the position, the trajectory of antimatter. In order to measure very precisely, you need to measure 1/100th of a millimeter. The most sensitive detector we can use are photographic plates. And what is shown here is a picture of an annihilation of an antiproton, an antihydrogen atom, inside a photographic emulsion. You can think of this as a transparent cube, that's the white bit, pierced by black lines coming from the point where the annihilation took place, on the surface or inside the cube. And it's really like a spider diagram, a star burst coming out in all directions as black lines in a photographic plate. Of course, in this image, it's very hard to see what this actually looks like. So rather than look at a still, I'd like to show you an image of a box, of a photographic plate, where you take off layer by layer by layer. And as you work your way through, the point where the annihilation happens becomes clearer and clearer. So this is really what you see if you zoom into a photographic plate with a microscope and go deeper and deeper and deeper until you see the point where the annihilation happened. You can see that as you go deeper, at some point, here in the center is a point where annihilation takes place. And from that point outwards, a bunch of tracks, a bunch of fragments, a bunch of white lines come out. And then there's a cloud of dots all over the place. These are just random noise in the photographic emulsion. They're just the grain of the photographic emulsion. In order to look at this, and it's going by way too fast for anybody to actually see what's happening, you can do something else. You can take this image, this cubic volumetric image now that you have zoomed line by line, and transform it into an object that you can look at from 3 dimensions. So in a way, a photographic plate, which is an inherently 2-dimensional object under normal circumstances, is being turned into a sculptural image. A sculptural image which is very similar to what you would see if a bug, an insect, is trapped in amber. In this case, what is trapped in the amber is the skeleton. And in fact, in this case, it's a ghost skeleton because it's what happens after the antimatter has disappeared and annihilated with matter. Let me show you what this looks like. You can actually see now in 3 dimensions where things are coming from. You can see the fat lines corresponding to a nucleus breaking up and these nuclear fragments flying around. You can see thin lines, dotted lines that correspond to the production of new particles and antiparticles. And you see a central cloud, a very dense cloud, which is where the antiparticle has gone into the photographic emulsion. And as it slowed down and come to stop, it releases so much energy locally that the photographic emulsion becomes completely blackened, and it's impossible to differentiate anymore the line of the antiproton coming in from simply the fragments, the short-lived fragments that fly outwards. It's only the long-lived fragments that you can see here, as well as the particles that come out in all directions. Now, this image was an image that is very recent. It's from a few years ago, but it was actually a process that was developed at the beginning of the 20th century in 1937 by Marietta Blau, who looked at these, or discovered these disintegration stars. In her case, it was not actually antimatter annihilating, it was actually particles coming from outer space. As these particles from outer space very occasionally hit a silver nucleus and burst it up, then this breaking nucleus fragments into different pieces. And these fragments, as they fly through the photographic plate, out from this point here, leave a trace of where they went through. Now, this is interesting because it was the first observation of the composition of a nucleus, but it's more interesting even from a conceptual point of view, because what this nuclear fragmentation actually is nothing else but nuclear transmutation. You're transforming a nucleus of silver into a nucleus of carbon, a nucleus of neon, a nucleus of nitrogen. This nuclear transmutation, the knowledge that nuclei can transmute, can be transformed from one to another, is of fundamental importance, in particular if you think of the time, 1937, and the general historical context in which this happened. There's another interesting question that you can then ask yourself with antimatter. I've showed you pictures of antimatter annihilating inside a photographic plate, but this doesn't have to happen. In fact, in my experiment, this will not happen. We will not annihilate the antimatter inside the photographic plate. We will annihilate it above the photographic plate, in which case you no longer see the starburst, the beautiful annihilation star that you can see behind me over my shoulder, but you will actually just see something like this, where a small piece of the shower of fragments will go through the photographic plate. Can you still call this an image of an annihilation? Well, in some way, yes, because in your mind's eye, you can extrapolate backwards the individual lines, and you can find the point where all these lines converge. This is the point of the annihilation, and such a point, such a tripod, can only come from annihilations. So if I now remove the help, the real image, the image of the annihilation, isn't actually what you see in the photographic plate, it's the image that you have in your mind. This is where images actually happen. And so, as for most other photographs, what we actually see is not the antiprotons, is not the antimatter. We see the memories of the aftermath of their disappearance. We see what's left after they've gone, after they have destroyed themselves and some matter. And I'll remind you of this again at the end when we come to Tomo's work, because in a way, what we did, what he did, is to look at this disappearance that happened without any observer. So at best, what is left is something that sticks in your mind. It's the memories, it's the aftermath, it's the disappearance. In our case here, you also see frozen time in 3D, because furthermore, the particles that go through the photographic plate are moving faster than the speed of light in this material. So you can think of these not as an integrating photograph, which is what normal photographs do. They just accumulate a certain amount of photons of light for a certain amount of time. These are instantaneous images. These are real instantaneous images. It's a compression of space into a flat map. And in a way, what it is flash freezing of space. The image is sculptural, and it's a single camera bullet time, which obviously is going to be a great conceptual playground for artists. And this is not surprising that artists are interested in this, starting when I first got involved in all of this in 2011 with Ars Electronica, where we have what could be called an artistic project, because it is a bet. It's a bet of how nature is going to behave between a collaborator at Ars Electronica and myself, And it's a motivation, it's a catalyst. It's part of the reason why the experiments that I am doing are actually taking place, simply because of a question asked by an artist. That was at the beginning. Now, a few years later, we've gone much further. And artists who have come to CERN in the Arts at CERN program have visited, of course, the antimatter factory, among them the semiconductor duet. This couple have been very interested by the photographs that I showed you, where we have many different layers of images. They've taken the individual images, they have combined them, flattened them, reworked them, made a huge mosaic out of all these images. And what you actually see here are the scratches, the conceptual scratches of the disappearance of antimatter across tens of centimeters, thousands of antiparticles having disappeared. This photographic exploration was also of interest to another artist, Linda Vreni-Nagler, who wanted to actually take a large number of photographs of an antiprotons annihilating inside photographic emulsions. The images we have, the images that I showed you, are all at the surface. And so we can go down, but we cannot go up above the surface. What she wanted to do is to inject antiprotons into the emulsion. And for that to happen, we needed an emulsion of about 400 micron thickness. Now, normal emulsion is about 2 micron thick. And so she had to first do an experimental exploration of how to produce very thick emulsions on glass plates. What you see on the left is part of the process where she is squeezing the gelatin into filaments that she will then melt onto a glass plate. The caliper on the right is what she used to measure the thickness of the photographic plate. And this was a 4-month-long exchange between her and me, neither of us knowing until the very last moment in 2018, which was the last time that this experiment could take place, whether the experiment would be possible or not. Here are the photographic plates that she ended up producing. And these were, of course, wrapped light tight and put inside the beam of antiprotons. What you see here is a vacuum chamber. Antiprotons come out of here. This is where her photographic plate was positioned so that the antiprotons would stop inside the photographic plate. And it's only if the photographic plate had the right thickness that she could see anything. If the thickness were too small, the antiprotons would stop in the aluminum foil before getting there. If the thickness was too big, they would not make it into this, to the glass support, and we would also not see anything either. Several plates were exposed directly into the beam of antiprotons. Several plates were exposed outside of the apparatus where millions of other particles would go through. The result of this exposure of the photographic plate was that all plates that she made showed nothing, except one. One plate, this one here, and you can see the problems that then happen when trying to expose this plate. It's so thick that the emulsion breaks, that there are structures everywhere, but you see something here in the center. This area here is where the antiprotons, the antimatter, should have stopped, should have annihilated inside the photographic emulsion. This is what we expect. Now, the trivial step now would be to take this photographic emulsion and look at it under a microscope to be sure whether this is antimatter or not. The much more interesting approach is to leave the photographic plate as it is, unknowing, undiscovered, whether this is actually antimatter or whether this is an artifact. This is where the plate is right now. It's not been studied, and I would argue very strongly that it should stay like that. And that brings me to Tomo Savic. Already before, you had seen the balloons. In fact, Tomo's question to me was whether I could use antimatter to annihilate matter. And when I said yes, he shipped me air, an empty space, an empty container, these balloons here, nicely bubble wrapped so that they would not be destroyed in a DHL sent box. The air is the air of a gallery of his. And these balloons, or actually half of the balloons, were then put, you recognize again the beam pipe with the antimatter, right where the antiprotons fly through. You can see it here again from the side. 2 balloons were exposed in December 2018. And I remind you, this was the last time that this was possible. This beamline no longer exists. We can no longer produce antiprotons that can be used to irradiate photographic plates or balloons. December 2018, and then January 2019, this is the outcome. The nice, shiny black balloon is the balloon that was inside the box, was the reference sample that I used in order to see whether any changes occurred to the balloon that was exposed, which is this one here. This balloon was exposed to antimatter. This balloon was not exposed to antimatter. A year later, January 2020, just before we had to leave CERN, the same two balloons again. This one here is now this balloon here. This balloon is now this one here. And there is still a difference between the two. They still are differentiated. This one has aged quite dramatically compared to its nice and shiny position a year ago, whereas this one here is almost not changed, with a slight aging, slight shriveling up, slightly less air than it had here. And so in a way, this experiment has shown that if you give an artist the possibility to play with antimatter, that artist will study questions of emptiness, of empty space, of what matter is, how to dematerialize matter, how to go beyond what matter is, and how to transmute matter. And so to finish, this is why I think anti is so important, not just to the scientists, but also to the artists. Thank you.
Thank you, Michal, for this very inspiring lecture. Yeah, I would like to just to, as we can see the questions of our followers, I would like to ask Monica. Actually, Tomo comes to the residency because you were in contact with Container, and usually how artists can come in art at CERN. Is there some competition, or you are choosing the artist? What is the process actually?
The process is we want to give the opportunity to everyone, and for that we have a number of call for entries competitions per year. When we collaborated with Container, this was in 2016, 2017, we sent out a call for entries for Croatian artists. This is part of our Accelerate program. It's a country-specific program that is only 1 year, only one edition, and the following year we move to another country. But we have also an international program every year, and anyone can apply from any country. And with this, we want to encourage the participation. We don't restrict to anyone. The artist doesn't need to have a PhD in physics or in science. It's a place that is challenging because of it's highly scientific and intellectual. It will be, in any case, an adventure for anyone who wants to be a bit outside of the conventional and usual spaces, but we want to give this opportunity to anyone.
Okay, thank you. So I have information that there is some question for Michael. Michael, you said that you have some extra laptop that you can check. Can you check the question?
But it's funny because I have my Facebook site on, but I don't see any questions. I see no discussion. So I only see no, I don't see anything here. I only see your website, and I was looking for the discussion, but I see no posts. How do I find the questions?
I don't know. Sanella.
This is all I see. No, I'm sorry. My background is, my face recognition is making it impossible for you to see what I see. But I only see the Facebook site without any further.
I'm seeing in my mobile at least one question.
I see.
It's for you. Do you want me to read it?
Yeah. Go ahead.
Oh, it's okay. I'll read it. It says, "Do you believe that science will ever give us an answer why the universe itself is completely asymmetric?"
So, yes, I'm an optimist. I think we will have an answer because all the ideas that people have come up with as to where this might be coming from are being investigated right now. We're looking at gravity with antimatter. Others are looking at the color of antimatter in comparison to the color of matter. With particles that we can produce, and others yet are preparing an experiment or several experiments looking for the oscillation between matter and antimatter. When I say oscillation, it simply means that a particle can transform into its antiparticle and back again. This is only possible if the particle is neutral. It does not work if the particle is charged, but there are a number of neutral antiparticles and particles, among them the neutrinos. Neutrinos are horrendously difficult to work with. They are able to traverse the Earth without interacting. But if you make a lot of them, then a tiny amount of them will actually be measurable. For example, if you look for the neutrinos coming from the sun and you have a swimming pool full of chlorine, then per day, 1 chlorine atom will be changed into argon. 1. You have to find 1 single atom per day. So you need very big detectors, you need very sensitive detectors, but these are being built right now. And it looks like, from an experiment in Japan, that neutrinos can oscillate into their antineutrino partner and oscillate back again, of course. If this is the case, then at least a mechanism will have been found that maximally breaks the symmetry. The oscillation likelihood for neutrinos appears to be maximal. And if that's the case, then we already have a smoking gun. We don't have the solution yet because you still need to find something that produces lots of neutrinos very early on after the Big Bang, but at least you already have an idea of a mechanism. And so I think that among the different paths that are being explored now, within the next 10, 15, 20 years, the situation will be much, much clearer. Now, from then on, you have to find a more detailed explanation. But if you already have a smoking gun, you've practically found the culprit.
Okay, thank you, Michael. So I really hope that your lectures, both lectures, will provoke further interests to connect these two parts, different parts, science and art. And I deeply hope that we will have new opportunity to develop the collaboration also with the artists from Zagreb. And I would like to say first thank you to Container to bring you to Zagreb on some way, and also to you for this wonderful lecture. So thank you.
Thank you, Radha.
Thank you.
The pleasure was mine.
Same here. I wish I had been in Zagreb instead of sitting in front of my computer at home, but yeah, that will happen.
Yes, so we all. Yeah.
Next time.
Okay. Next time, yes, let's say. Okay, thank you, guys. Okay.
Thank you.
Bye.
Bye-bye.
Ciao.